Welcome to the Big O class. We've got front end and back end together in our 2011 cohort. We're going to take like 60 seconds. Want you to just write out for yourself, and then we're going to discuss as a group. So write out for yourself, what is an algorithm? And what do you already know about Big O notation? And could you describe it to somebody non-technical? If you don't have an answer for that one, that's okay. But what is an algorithm? And then what do you already know about Big O notation? And could you describe it to a non-technical person? Take like 60 seconds, write out some notes for yourself, and we're going to discuss as a group in a moment. All right, so let's talk about it a little bit. So what is an algorithm? Could you share some ideas about what an algorithm is? Any volunteers for me? I want to get started. I have a preference to just raising your hand in Zoom. You're also welcome to DM me things in the Zoom chat as well. If you don't want to like answer publicly, you're welcome to DM me privately. Always happy to take questions and answers that way too. Let's start with Ben. Ben, what's an algorithm?
An algorithm is essentially just a set of instructions to be performed on whatever you give it.
Okay, a set of instructions. That's good. Give me like a real world example of like an algorithm.
Would you ask me or somebody else? Did you want me to keep
Yep,
going?
asking you. Yep. So a set of steps
Okay,
to
there we go. Mic's
perform.
working. Well, at a high level, you have some algorithms that are like made to do some complex things like recommend videos on YouTube, but you can also have an algorithm just be like a for loop that does a thing like adds one to a number every time, or whatever you decide to do.
Yep. Yeah, if we think about like a non-technical application of what an algorithm is, I like to think of recipes. So what are the steps for a recipe? You know, crack an egg in a bowl, whisk in some sugar, until firm peaks and then make some meringue or something like that. In the Zoom chat, as well as each of your channels, I've also pasted a link to a shared Google Doc where we can all take notes. You'll all have edit access in here. I'm going to have a slide deck going in a little bit. I'll share those slides. So yeah, that's a good start. So an example would be, let's see. So when I think of an algorithm, like another real world example I like to think of is like telling my kids to go clean their room. The first couple of times I had to walk in and say, okay, pick up the clothes off the floor, put the books back on the shelf, put your toys in the toy box, like make your bed. And now I can just say, hey, go clean your room, and they know what I mean. And so over time, we can adapt these algorithms into like higher level functions or higher level instructions of go clean your room. And, the computer kind of knows what to do, or in this case, my kids know what to do. Well, they know what to do. They don't always do it. And so, yeah, I think this like just calling an algorithm a set of steps. I think that's a good start. Does anybody else have any ideas on how you could define an algorithm, either to a technical or non-technical person? What other ideas? Is a method an algorithm? Kind of. I mean, a method implements an algorithm. We could think of it that way. So I could write a method that says go clean your room, and it's got the list of steps inside. And so clean your room as a function is actually performing that algorithm of all of those individual steps. We could have an algorithm of bake a cake, and it's got all of those steps. So yeah, we could think of a method as an implementation of an algorithm. Someone DM'd me, an algorithm is a way of turning data into information. I think data kind of is information. So an algorithm would be a way to like process that data into maybe a different kind of information, or process data to tell a story of some kind. But data and information are pretty interchangeable in what we do as far as terminology there. No other hands raised, but I'm getting lots of DMs, so this is great. So give me a moment to catch up here. So an algorithm is a structured pattern that analyzes input and delivers results. I like that one. That's a great one. I'm going to put that one in our Google Doc. What else did I get in here? An algorithm is supposed to keep going, no defined end. Typically, no. Typically, like there's an end to it. Like we know when it's over. We know when it's finished in some way. Yeah, these are great. So again, please, you're welcome to DM me anytime. Someone just dropped into chat a whole bunch of categories of algorithms, which are great. Binary search and sorting, those are all algorithms. So yeah, they're just names for like a collection of steps of instructions. Cool. All right, well, let's go to our second warm-up question. What do you already know about big O notation? And could you describe that to a non-technical person? Anyone on the front end team? So we've heard from back end. Anybody on the front end team? Let's go to Matt.
I would say that big O notation is a way of measuring the efficiency of algorithms by graphing them, basically. So some algorithms are more efficient than others, and big O notation is a way of figuring out which ones are most efficient or least efficient.
Okay. Yep, so measuring the efficiency of an algorithm. Okay. If you had to describe that to someone who didn't understand those words, can anyone think of a good analogy of like how we can compare the idea of big O notation to something else real world? And we will get into the efficiency graph over the course of the morning. Let's go to Adam.
So you could use like someone trying to find a name in a phone book that was like started with the last name letter T, and an algorithm that's really efficient would be able to get to that in a short number of steps, whereas a bad algorithm that's really inefficient might just look literally on page after page until it finally got there.
Okay, so so an example would be looking up a name in a phone book versus page-to-page search. Yep. Great. Anybody else have any other like analogies, examples of how you could explain big O notation? I got a DM how expensive an algorithm is. So sometimes when we talk about expensive, we talk about CPU usage or CPU cycles, which you could equate into electricity usage and the cost of the hardware and literally come down to a financial expense for things. But yeah, the expense of an algorithm, how expensive something is, that's a good one. Highway traffic as an analogy. If you want to share a little bit more about that, I'm curious how you would think of highway traffic around like big O notation efficiency.
I was just thinking about like speed and how the volume affects the speed of the traffic.
Okay. Yeah. Okay. That's actually a pretty good analogy when we think about the fact that a big O notation is about processing a quantity of data typically, and we want that to be as efficient as possible. So if we think of the amount of data as like the amount of cars, then a wider freeway is going to be better because we can get more cars down the freeway in the same amount of time. Yeah, that's an interesting analogy. Let's go to Max. What do you got for us?
So way of calculating or measuring like time or the amount of work a system's going to have to do like exponentially. It's like if you have an array of 10 things, it's like, oh, I have to do 10 things. But if in that array, each of those 10 things had 10 things inside of it, it's like, you're not just multiplying. Normally it's like, it's 10 times 10. And then it's like each of those 10 things had 10 things, like it's an exponential growth, I think.
Mm-hmm. Yeah, and we'll definitely get into like some of that terminology. So that's a good one. Another one that I like to use is talking about horsepower with cars. I don't know very much about cars at all. I'm not mechanically inclined whatsoever. I did some web development work for Mitch Hedberg back in the day, and he had a joke about how, like, if the gas gauge doesn't say E, like, I'm in big trouble because that's the only thing I know how to fix. So I'm going to grab my toolbox, aka wallet, and like put more gas in the car. So I don't know much about cars, but if you know anything about cars, if you've looked at cars or learned anything about cars, and we talk about horsepower, like more horsepower is better, less power is like not as good of a car. And we can kind of think of algorithms in the opposite sense, where lower is better, and so less is better when it comes to an algorithm. But we can kind of use an analogy of horsepower to talk about like how powerful is an algorithm, or like many others have said, how efficient it is, how expensive it is. So all the terminology that you've brought up so far, spot on. This is great. Love it. More Mitch stories. I'll see if I can drop the occasional Mitch Hedberg joke in there if you like. Although he does cuss a lot in his jokes. All right, so let's talk about like kind of the main points here. So I've got a slide deck that I'm going to share, and I will drop the slide deck in our first palm break. But for now, I just want to get through a couple of slides. So we're going to talk through some terminology and theory. We're going to have some more group discussion kind of as we go. Ultimately, what I want to get to is some interview challenges and show you kind of my process for some pseudocode, and how I would analyze the big O notation of the pseudocode that you all are going to come up with as we work through a couple of technical challenges. But please, please, please ask questions throughout. I love taking questions on this stuff. My goal is to get us out of here before 2 hours is up, because I know that you got projects and stuff going on, you got finals coming up. So I don't want to take up your entire morning. If I can give you some of that time back, I would love to do so. But please feel free to ask questions as we go. All right, so we already talked about our warm-up. So the main idea here of like why is this important for front-end developers? And I want to like cover this early in the chat. This is really about differentiation. And this is something that I talk about a lot in different kinds of classes. If you can speak to this during an interview, you really stand out against like other candidates who maybe don't study this kind of stuff. There are boot camps and programs that don't cover this kind of topic. And part of me coming to Turing was to be able to introduce these kinds of topics to the students, because even though you might not get asked about big O notation in an interview, if you can volunteer it in an interview, you're gonna like blow their minds. Like if they give you a technical challenge and say, how would you solve this? And you like write out some pseudocode and kind of look at it and go, this is going to be like n log n because of the way that I've structured this. And they're going to be like, big O notation, like check. And it's going to like super impress them. You may never get directly asked, do you know about big O notation? Or can you analyze this algorithm for big O complexity? You may never get outright asked, but if you can volunteer it, you're going to be miles ahead of other people. That said, today is an introduction. You are not expected to be an expert on this by the time you get out of Turing, certainly not by the end of this morning. But today is just about introducing you to the terminology. We did a data structures class yesterday with the backend folks, and I recommended to them afterwards, like, hey, this would be a good video to go back and watch and good notes to go back and review over intermission, because you're going to be interviewing soon if you're not already interviewing. Some of you are already interviewing for jobs. And so the sooner we can get this into your noggins to where you understand what these terms mean and why we're learning this, the better off you're going to be in order to be able to speak to this stuff in interviews. So this is all about differentiation here. Someone asked in chat if I could share that data structure video with front end. Absolutely. Yeah, I will drop that in your channel later. Cool. So you're also going to get more big O in mod 4. So this is just meant to be an introduction. You're going to get a little bit more in mod 4. Hey, that rhymed. So yeah, you're not expected to be an expert as of today. We just want to introduce the terminology. So some misconceptions about this. Common thinking is that big O is more back end than front end. I like to tell folks that, like, if a back-end developer writes inefficient code, they slow down one tab in my browser because they've slowed down a server somewhere and that browser tab is still spinning. But if a front-end student writes inefficient code, they slow down my entire browser because you're using my CPU, you're using my RAM to run your code. And so if you write really inefficient code, you're causing like a bad user experience across my whole computer, not just one little browser tab. And so front-end students actually wield a lot of power when you think about it that way. Infinite loops are a feature, not a bug. What if we both write bad code? That's bad. That's exponential, and we'll talk about that in a little bit. But when I drop these slides later, I'll let you read through this. These are some links to some websites and some news articles about how these websites were actually affected by a JavaScript library that somebody figured out. And there was one website, it wasn't specifically YouTube, but there was a news website that basically Friday afternoon, somebody managed to inject a JavaScript library that over the course of the weekend until everybody got back into the office on Monday, customers were complaining like crazy. Like, I'm just trying to read the news and the fan on my computer kicked in and everything got really slow. Somebody wrote a JavaScript library to mine some kind of cryptocurrency. It wasn't Bitcoin, but it was mining cryptocurrency in JavaScript using everybody's machines that was visiting that website. And that JavaScript library actually got really popular, and it ended up on 4,000 government websites, as well as other big names like Oracle and Tesla and Starbucks. And it was on YouTube briefly. So anybody watching YouTube was also like mining some kind of cryptocurrency because of this JavaScript library. And it's still out there. It's still out there. And so as a JavaScript developer, you've got access to a lot of hardware that sometimes a backend developer doesn't even have. And so it's important that that we also understand that, like, this is also important for front end students. I don't encourage you to go write a JavaScript library to mine, Bitcoin or anything, even though it's, like Dogecoin is like going through the roof lately, but it's an important thing to understand. So, all right, so moving on from here. So the big idea around big O is we're talking about time complexity, how many steps that an algorithm is going to take to process some quantity of data. So folks want to like add some of these notes into that Google Doc. That would be really helpful for everybody. And that way y'all can share this Google Doc later with the YouTube video, and I'll put the YouTube video for this class into this document. So you've got that all in one space. But we talk about time complexity and space complexity, and you can tell the nerds came up with these terms when we talk about time and space. But when we talk about time, we're generally talking about CPU. And when we talk about space, we're talking about RAM. So let's add some of this into the Google Doc here. So the main points are time complexity and space complexity. Oops, complexity. And time complexity is going to be about CPU usage, and space complexity is going to be about RAM usage. And again, feel free to pause and ask questions and so on along the way. All right, any questions on this so far? I know we've been kind of like throwing a lot of terminology at you in just the last couple of minutes alone, but any questions so far on this? Nothing so far. I like to wait an awkward number of seconds just to be sure. My students know I will just stand here and sip my coffee. All right, we'll move on. Let's take time. generally when we talk about big O notation, we always talk about worst case scenario. So what is the worst possible outcome given like some quantity of data? Generally, we would say something like, if you've got to look through an array to find a value, always assume it's the very last thing in the array. So as you're iterating over it, it's always going to be the last thing that you find. So whenever we're calculating big O, we always calculate the worst case scenario. It's usually better than that. We call that average case. So there's worst case and there's average case. Average case is like, yeah, but you know, most of the time it's going to be this. But when we calculate big O notation, we always talk about worst case scenario. So we can do things like caching and other optimizations and shortcuts and guard clauses and whatever to reduce the likelihood that we're going to get to that worst case scenario. But when we calculate big O notation, we should always calculate our worst case scenario. Like if nothing is cached, nothing's in the database, and we've got to like search and scan through a whole bunch of data, what's the worst possible amount of time and space that we need to actually go get that bit of data out of memory? So we're always talking about worst case scenario. So I'm just going to add this in the Google Doc here. So we're always talking worst case scenario. The other thing to note here, when we talk about big O notation and analyzing things, we only analyze one method at a time. Because when you think about how like a whole application gets built, this method calls this method, and that method calls like 5 other methods, and those each call like a bunch of other methods, and then you're calling in like library code and so on. So we never analyze everything from like a whole application point of view, because that would be like a ridiculous amount of CPU usage. And so we only analyze one method or one function at a time. And we say, what is the efficiency of this function? Can I improve that in any way? Because sometimes just improving one function can have kind of a cascading effect that improves the efficiency everywhere else. So if you can narrow it down, like this function is a bottleneck, this function is like really, really slow compared to everything else. If you can improve that, sometimes that makes everything a little bit faster. So we only analyze one function at a time. All right. When we talk about notation, this is where things get a little mathy. We use capital O, and O doesn't really stand for anything. Some people think it's like the number of operations, which is okay to think about. And so we always use a capital O when we talk about big O notation. And so I'm just going to add some notes here. So we use capital O to start the math function writing. And then we use a lowercase n to talk about the quantity of data. Now, sometimes we're comparing different data structures. And so sometimes you'll see people use like the letter N and the letter M to differentiate between two different data sets when you're comparing, like, because I'm looping over this data, and as part of that loop, I'm looping over this other data. How do we multiply those things together, as someone mentioned earlier? And we'll talk about N times M in mod 4. But for the simplicity of what we're doing today, we're just going to have like single data structures. And so we're just going to use N to sort of replace the number of things that we have. So you could think of N as short form for like the number of elements in our data structure. So how many things do we have in an array? Or how many keys do we have in a hash? Or how many attributes do we have on an object? That's where we would come up with the letter N to say, if I had to iterate over all of those things, how would I calculate this math function? And we're going to go through the terminology for some of these throughout the morning, right after a pond break that we're going to take in a little bit. And if we have to do something more than one time, if we were to write down and say, well, we're iterating over this array, and then we iterate over the array again, then we iterate over that array a third time, we could calculate it and say this is O 3 times N. But that 3, because that's a constant value, like it's a number, it's actually like a digit, we usually just drop that out. We call it a coefficient, and we actually drop the coefficient on there. And so we would just say it's O of n. So I'll add that in the notes here. So we don't count coefficient numeric counts of processing. And someone asked in chat, I think the O might stand for order, as in the order of n squared. It could be. It could be. I haven't seen a good definition like this is why we use the letter O. So it could mean the order of operations. Yep. So thanks for sharing that over chat. O for oh no. No, don't think that, please don't think that. Sometimes these CS topics can feel a little scary because it's drastically different from other stuff that we teach at Turing. But we do want to introduce this stuff just to better prepare you for interviews. If you hung out in my fireside chat a couple of weeks ago, or if you've done other classes with me, you know I want to see you succeed out there. I want to do everything I can to help you get through those interviews. And this is why we want to cover these kinds of topics, because we want to give you the best shot possible of getting those jobs. So if you can speak to this stuff even a little bit, like in that interview, if you're like, yeah, this algorithm, it looks like it's going to be n squared. And they're like, you know, big O notation. You can say, I had 2 classes. This is literally the limit of my knowledge. This is all I know. That's fine. Like the fact that you even brought that up in an interview is going to impress them and wow them. And so again, we don't expect you to be experts on this, but we do hope that you'll remember the terminology so that you can speak to it. If you get asked, you can at least speak to it a little bit, or preferably volunteer it. If you can feel confident enough about it to volunteer it in an interview, it's going to really set you apart. So some other common examples, and these are the ones that we're going to go through today. We're going to talk about O of n, n squared, log of n log n. There's another one that's just O of 1, which is just a single operation to go do something. And we're going to go through and dive in on what each of those mean throughout the morning. All right, any questions on this notation slide? Because this is some important stuff that we're going to need to know in order to kind of move on in our notes. Any other questions? So you can feel free to raise your hand, you can DM me in Zoom. Any other questions before we move on? You're all very quiet for a Thursday morning. All right, let's go to Alex for a question. What do you got, Alex?
This is sort of related, but in the developer tools, like in Chrome, like the Lighthouse option that we usually use just to like determine accessibility, there is a tab for performance. Is that doing something like this, like under the hood?
That's a great question. As I remember, the last time I looked through that, it's really the performance there is actually looking at strict timing. Like this function took milliseconds, this function took more milliseconds, this function took milliseconds. That can help you identify where your slow code is. And then from that output, you could then go do a big O analysis on that function and go, well, this function took like several seconds where everything else was taking milliseconds. Why does this one take so long? You can kind of go through and do a big O analysis on just that function and see if there's something about that you can improve. Like, are you doing something like over and over again that you could clean up? Are you doing like a map, and then inside that map, you're also looping over things, and inside that loop, you're doing like even more things? Is there a way that maybe you're calling another function over and over again when you don't need to? And those are all different ways of sort of reducing the amount of time that function takes. So as I recall, the performance tab in the inspect tools is just giving you like literal timing of how long things take. I don't think it's really going through and doing like big O analysis. It's literally just timing, like I spent this amount of time running this function and like loading these assets and things like that.
Okay, thanks.
Yeah, no problem. Thanks for asking, Alex. I had another question come in on chat. Do we use these notations to describe both the space and time complexity, or just one at a time? That's a great question. My next slide is about space complexity. So we also use a similar notation for space complexity. In the past, I used to say, you know what, just use a multiplier. Like if you're adding another hash, you're like doubling your space complexity. If you're adding another object, you're doubling your space complexity. We can also use like big O notation when we talk about space complexity. We can say, oh, well, I added another hash, so that's another O of n. And so we had the original data, we added another data structure, and so that's technically 2n, but because we drop those coefficient constant numbers, it's just O of n as far as space goes. So we drop those coefficients. But yeah, we can use the same like big O notation when we talk about space. It's also appropriate to say, like, you know what, we're doubling our memory usage or we're tripling our memory usage because of how we're tracking something in memory. But the key thing to remember here when we're talking about space complexity, and this is the only slide I've got on space complexity. When we talk about space complexity, we don't track individual variables. So if you say like var a equals 5, we don't count a really towards our space complexity because a is just a single value of some kind. But if you said a is an array, now we're building another data structure kind of on purpose. And because we're building another whole data structure on purpose, we count that towards our space usage because you're tracking more than just like, you know, a equals b plus 5. And so when we talk about space complexity, we're generally only counting additional data structures or objects as we process our data. So we don't count variables, we only count new data structures. Cool, thanks for asking that question. All right, so we're gonna take a palm break and then we're gonna basically go through some quick charts, and this is just gonna wrap up the terminology, and then we're gonna get into those tech challenges. So we're gonna do a 5-minute palm break. We'll come back at 38 minutes after the hour, and we will continue from there. We'll see you at 38. Resume recording. All right, I neglected to record right after coming back from palm break, so I'm just going to cover these again real quick, just for the sake of the recording. Go backwards, not forwards. So the first one we talked about was linear time, and these are operations that have to iterate over an entire data collection. And in the Google Doc, you'll see some notes that folks are adding around this. From there, we talked about quadratic time, which is typically where we find things that are nested. Quadratic time is not necessarily a bad thing. Sometimes quadratic time is the right answer to a technical challenge. Generally, we want to try to avoid it if we can. From there, we talked about kind of plateauing data, which is logarithmic time. And we used an actual dictionary as an example of, like, you know, you open the book in half and then you figure out which half you look at from there, and you split that in half, and then you split that in half. And so the idea with logarithmic time is every step you do, you're cutting out half of the work. From there, in between linear time and quadratic time, we talk about n log n. And this is where our really efficient sorting algorithms come into play. And so as they process through the amount of data that we have here, we're saying for everything in that array, how do we do that log of n to figure out like how to sort that data? And so the linearithmic time, as we call it, we typically just say that's going to be like a sorting algorithm. Although sometimes you can do a search of your own. And so it's not necessarily a sorting algorithm. You can also have some search algorithms where you can say, for everything in this array, I want to do a binary search, which is a logarithmic time operation. I want to do a binary search on everything that's left to try to find like a counterpart or something like that. And so that can be n log n, which is better than n squared. Someone says I have to tell my joke again. Okay, fine. So for the sake of the recording, when we were going through the dictionary, I was trying to find the word pterodactyl, and I told the joke, why can't you hear a pterodactyl go to the bathroom? Because the P is silent. All right, moving on from here. Our best case scenario, kind of the holy grail of big O notation, is something we call constant time. That says no matter how much data we have, it takes exactly one operation to go find what we're looking for. So constant time, we write out as just O of 1. And that's just constant time. Oops, Didn't mean to advance the slide there. So some examples of this, just simple math operations. 5 plus 5, that's O of 1. Calling a function, we would say, well, that's O of 1 because we would analyze that other function later. But for now, that's just one operation. It's one step that happens. Accessing an array by an index position. If you know the index position, say I want to go to the 5th element in that array. Now I got the 5th element movie stuck in my head. If I want to go to the 5th element in an array, I can jump immediately there in one operation. If I know the attribute of an object, I can immediately get its value out of memory. If I know the key in a hash, I can immediately get its value out of memory. Although we talked yesterday about how a hash, it's got to go through a hash operation, which is math. That's O of 1. It does like sort of that bucket lookup. That's also O1. But from there, it's got to maybe look through a linked list. In a linked list, searching through a linked list is going to be a linear operation. But we talked yesterday how in a hash or in JavaScript, a map, hopefully you don't have many collisions in there. And so that linked list hopefully is very short, maybe only 1 or 2 things. And so it's on average, only one lookup from there. And so we just say, well, it's a whole bunch of like 1 lookups. And so therefore it's just O of 1. And so no matter how much data we have, no matter how many attributes we have in that object, no matter how many things we have in that array, if we know the position or we know the attribute name, we can get there in one step, and we call that constant time. This really is a best case scenario. And so if you want to add some other notes in here, like when we talk about constant time, just doing math, calling other functions, accessing in arrays by index, or accessing an object or hash by a key or attribute. If you want to add that into the notes, that would be super helpful too. Thank you. All right, so from here, let's go through. And so, I mean, these are all of our operations. So I'm going to leave this on the screen for a little bit. What I would like to do is get you into some breakout rooms. But I need to go build a poll real quick. So I need to stop sharing this for a moment. Pull this over here. Actually, before we go into this next part, I want to talk about this. So we talked about early on, like, you know, if an algorithm you come up with is n squared, that's generally okay. Even if I say like, hey, you got 1 million things in an array, how would you process this thing? If your algorithm ends up being n squared, that's generally all right, because I'm a big fan of the saying done is better than perfect. If you can find an algorithm that solves a problem, great. You solved the problem. That's better as an outcome in an interview than not solving the problem. And so any way that you can solve the problem is good. But when we talk about, you know, the like overall time complexities, if you've got a very small amount of data, if we kind of zoom in on this part of the chart, if we have a very small amount of data, it really doesn't matter how complex our algorithm is, because everything in this little box here in the bottom left of our chart is going to run really fast. So JavaScript, for example, it actually implements 2 different sorting algorithms. And so when you say, hey, go sort this array, the first thing JavaScript will do is look at the size of the array and go, it's small. I'm just going to do like a bubble sort. And it's going to run an n squared sorting operation because it's easier and it's so small that the amount of time it takes is negligible. But if that array is really big, it'll be like, all right, fine, it's big. I need to use this other algorithm instead because it's more efficient. Python does the same thing. Python will also look at the amount of data and then figure out which sorting algorithm to use. Ruby only implements 1. And so no matter how big or small the amount of data is, it's always going to run the same quick sort. But my point here is that when you're facing a technical challenge and you're writing out the steps that you think you're going to take and you're trying to analyze big O notation, it's okay if it's n squared. It really is, because the best answer that you can come up with in an interview is a working answer. So just get it working. Implement whatever you need to get it working, and then figure out whether there's a way to optimize from there. All right, so we got through all of that. So we're going to do some breakout rooms, and then what I'm going to do in these breakout rooms is show. So I'm going to have you choose between 1 and 4, like numbers between 1 and 4, and this will determine which tech challenge you're going to work through to get started. So give me a moment to build out this poll, because it doesn't let me reuse a poll every time I teach this class for some reason. So choose your own adventure. I will make it anonymous, so I will not know who votes for what. But let me go back and find another slide deck. Where did it just go? That just disappeared on me. There it is. All right. So problem one. Let's also pause here for questions as well. Are there any questions about that chart if we go back to that chart? No questions? You're also quiet on a Thursday morning. Doug, you got a question? What do you got for us?
I think I know the answer to this, but I just kind of want to clarify. Previous, when you were talking about if we had like O times 3n, we would drop the 3.
Mm-hmm.
Is that because while it will take 3 times longer than just O times n, it doesn't change the shape of the graph? So as far as we're concerned, you're just 3 times further along the same line.
Yeah, so when we talk about this graph, that's exactly right. We're just doing this linear operation over and over again. And so, you know, it's not as bad as n times log of n. And so it's still pretty close to being linear time. And so we would just say it's still a linear operation. So as long as those iterations over that array aren't nested, and we're just like iterate over an array, iterate over the array again, iterate over that array again, we would just say, okay, it's a linear operation because you're iterating over the data, but it's not nested. And so we don't have to multiply those things together. And so we just drop the constant value that we call a coefficient there. All right, so here comes the poll. These are the 4 challenges that we're going to start with. And while you're voting on that, we'll go to Ben for a question.
I just would like to clarify and see if my understanding is correct on the difference between, or like easily identifying if something's log n log n or log n. And is it because you're like log n is doing it once, and then n log of n is doing a log n action n times, like if you're doing it. So is the n log n still technically a nested iteration?
Typically, yes. So a linearismic time, which is this part of the graph right here, you're basically doing a linear operation. And for each thing in that linear operation, you're doing some other logarithmic operation on the same size of data. So we're still using the same value of n. So let's say we had 1 million things. So in that 1 million things, we're going to go do a binary search on that same 1 million things. But we have to do that for each of those 1 million numbers. For each of those 1 million numbers, we're going to do like a binary search on the same array. Then that would be a log n, but we're doing that log n for each of the n things. And so we multiply those together, and that would give us our n log of n. All right, so we got 49 of 51 people voting. So I will, oh, there we go, 50, 51. Oh, we might need a tiebreaker depending on how that 51st person votes. Nope, we don't need a tiebreaker. So everybody wants to detect a palindrome. That's going to be our winner by a very slim margin. So let me get that slide going here. Actually, what I'll do is I will drop this in your channels. And I'm going to put you in some random breakout rooms for a little bit. And what I want you to do is just think about the algorithm from a very high level point of view. Think about it like a recipe, crack an egg in a bowl, just very high level generic instructions like loop over the data or loop each character, things like that. It's not about actually writing the code. It's not about actually solving the problem. I just want you to come up with high level pseudocode, okay, which is just the algorithmic representation in very simplistic language. I want you to come up with just pseudocode. And then when we come back from the breakout rooms, I'm going to call on some different rooms to ask you what your pseudocode was. I'm actually going to write out the pseudocode and show you how I analyze the big O notation. And then we'll kind of like write out little tables for those. So let me make some breakout rooms. Let's see, we got 50 odd people. Let's do, if I do 12 rooms, 4 to 5 people per room. Let's do 20 rooms. We'll do 20 rooms. Now we'll grab a big fat nerd dice of 20 sides to call on rooms when you get back. So I'm going to give you 10 minutes to think about this one. Actually, I'm going to give you a little bit less than that. I'm going to give you 6 minutes to think about this. And then we're going to come back after that. So let me drop the prompt in your channels. So 2011 backend and 2011 front end. All right, so the prompts are in your main Slack channels. Basically what we're looking at here is a string like Mr. Owl ate my metal worm. That's technically a palindrome, which means if I completely reverse that string, it would read the exact same way. Rye Mellow Mama Otter is not a palindrome, but it actually uses the exact same letters as Mr. Owl. And so what I want you to do is write me a function that takes in a sentence, takes in a string, and returns just a true or false if the letters could be rearranged into a palindrome. We don't want to know what the palindrome is. I just want to know, could this string be a palindrome? All right, so I'm going to give you just a couple of minutes to think about this in your breakout rooms, talk with each other, figure out how you would solve this with one another. And I'm going to call in some rooms when we come back in about 6 minutes. So we'll see you back in a moment. All right, welcome back, everybody. All right, so let me pull my breakout rooms back up here. And I'm going to roll my big giant metal nerd dice. And we're going to go to room number 8. Room number 8 is Jessica, Jolt, and Trevor. So what kind of high-level instructions would you come up with for solving this problem?
I can read off our pseudocode since I wrote it.
Yeah, great.
Yeah, so we first said get rid of all the spaces.
Okay.
With a string.
Okay.
And then we would check the length of the string for how many characters are inside of it.
Okay.
And then if the length is even, we would check that all the letters occur an even number of times. And then if the length is odd, check that no more than one letter occurs an odd number of times.
Okay. So tell me a little bit more about do all the letters occur like an even number of times? So how could you break that down into just a couple of more steps?
Not sure.
Okay.
Do my partners want to jump in?
Yeah. So we could say do all letters. So we'd have to like iterate over the characters. And then in that, we would like count how many times they exist, something like that. Sorry, I missed who else unmuted, but if you've got other ideas.
That was pretty much what I was gonna say, was iterate through and one and count how many times each character occurs.
Okay.
Yeah.
So we could do, so afterwards we could say if length, if string length was even, does everything have even count? This would mean we'd have to like iterate back over how we counted those things. So we could track this in an object or a hash for each character, and then just keep like an increasing number for each of those. And then later on, we'd have to iterate over each of those keys or each of those attributes. So we'd iterate over the keys or attributes, looking for odd or even counts, versus our string length. So something along those lines. All right. So as I write out my pseudocode, I like to indent things so I can kind of see how things get nested in here. And so removing all the spaces from a string, if we had to iterate over that whole thing and strip out all the strings, strip out all the punctuation, that could be a linear operation for each thing that we want to remove. So what I would probably do is inside of this iteration, I would just say skip the spaces and punctuation, because we still have to iterate over that stuff, but we might as well do that while we're counting everything. And so this is how I would go through and optimize this as well. And so now getting the length of the string in JavaScript and Ruby, getting the length of something is generally going to be an O1 operation. So this is going to be a constant time operation, iterating over every character in that string. What kind of time operation are we looking at to iterate over all of our characters? So we got some stuff dropping in chat. All right, so we had O of n dropped in chat, and that's right. So iterating over every character is a linear operation. Now inside of that, we're skipping our spaces. That's going to be an O1 operation, because we're looking at the character and say if it's a space, whatever, just skip it. We'll just move on from there. Otherwise, we have to count how many times these exist. So we want to track occurrence, occurrence in an object or hash. I spell occurrence wrong. There we go. So putting something into an object, putting something into a hash, we already talked about earlier, that's an O1 operation as well. So because these are nested, we multiply these together. And so we would say we've got O1 operations, but because they're happening inside of this, we would take the worst one of these. So this is O of 1, this is O of 1. Therefore, we only count it one time. And so we'd say, okay, well, inside of the loop, we're dealing with an O1 constant time operation inside of here. And 1 times n is just n. So far, we've got just an O(n) operation. So now I would look at, okay, well, what's happening in each of these steps? So if we have to iterate back over those keys or attributes, this is going to be another O of n operation. And then looking for even and odd counts versus the string length, that could just be an O1 maybe operation later on. Like, is this odd? How many other odd numbers have we seen, and so on. So that could just be an O1 operation. So if we look at everything at sort of what I call this indentation level here, these are all happening at that same indentation level. Therefore, we just pick the worst one. This is how I work out my big O notation. So if we look at these steps right here, we've got an O1, we've got an O of n, and we've got an O of n. O of n is the worst one. And because we don't count it twice, so we would say like some sort of tracker mechanism we had an O of n time complexity. But because we've added another data structure to track this stuff, we could say, well, I've doubled my RAM, or in this case, I've got linear space complexity, because we've added another data structure where worst case scenario, every character in that string was different. And so now I've got a hash with all of those different characters as attributes, or I've got an object with all of those other characters as attributes. From a time efficiency point of view, we're not going to do better than this. Could we do better with our space operation, though? Is there a way that we could do this where we're not introducing more space complexity? So that was a great algorithm from that team. So good job coming up with that. Did anybody else come up with anything different? Should I call in another room, or do we have any volunteers? Got a volunteer from Jesus. What do you got?
Read the input string.
Okay.
We're gonna remove the spaces from the input string, and then we're gonna set a variable. I call it a check string, just an empty string. And then we're gonna iterate over the input string while more elements exist. Grab and remove the last element of that input string, and then add it to the new input string, being the last element that gets added in there, and then check the equality of both.
Okay, so we have one input string coming in.
Mm-hmm.
And so similar to before, we're going to skip spaces and punctuation and things like that. Right. From there, what were we doing? You were talking about having a second string.
Yeah, it's just an empty variable.
Okay, and what were we putting in there?
For now, nothing. Oh, wait, you're already iterating over it? So then we will grab on our loop, we're going to iterate over the input string.
Yep. And so for each of those characters, what are we going to do?
So now we're going to look at the last element of the input string. We're going to grab that element and remove it and add it to the new string or empty variable that we have at the very beginning. And then
so we're iterating over our characters, and for each character, we'll just call it CH. So are we putting CH into that new string? Because you made it sound like we're grabbing the last thing and adding that in there. So I'm a little confused over that step.
Yep. So the character that you grab, the last character that you grab from that input string, you're going to add it to the empty variable. And then keep doing that until there is more characters in the input string. And then at the end, just check that they're both the same, that they're both equal to each other. And that should give you your true or false. Does that make sense?
If we're iterating over, in this case, Rye, Mellow, Mama, Otter, this is the only input we're getting. We're not getting both strings.
Right.
We're just getting one string, and we're trying to check whether this could be a palindrome. And so we get a W.
No, first you get the R. So it would be, because you're looking at the last element. So the R, and then you add that to the new string. So the first letter on that new string becomes R. And then the next one will be E, and so on and so forth. And then at the end, you check that they're both the same.
So
it's like reversing the string kind of.
Right. So that's not what we're looking for here. We're basically saying, based on this input string, if we were to rearrange these letters, could that be a palindrome? Like because Mr. Owl ate my metal worm, if we take out all the spaces, it's the exact same quantity and the exact same letters as this sentence. And so what we want to know is, aside from the spaces, if we took all the spaces out of here, could we rearrange this second string? Could we rearrange all of these characters to create something that would be a palindrome? And so we want to know, could we rearrange this into something that was Mr. Owl? Because just reversing the string, that's checking whether it is a palindrome, but we want to know, could we rearrange these to become a palindrome?
Got it.
That's what we're looking for there. So yeah, a big important thing with technical challenges is making sure you understand what it is you're doing. So always ask good clarifying questions. Like, is this what you mean? And they'll always clarify for you that what they meant. Let's go to Ben for a question and then Matt.
I was gonna go for another algorithm, but I also have a question. So
okay,
and
let's go with questions first.
Okay. In terms of, this is kind of specific to Ruby.
Okay.
Is the .chars method, is that like performing an iterative over the entire collection, or is that just creating new space?
So when we have a string and we do .chars, that's technically turning this into an array of individual strings. Lower level languages, a string is technically just an array of individual characters. But in Ruby, this actually produces an array of smaller strings because everything in there is still a string type, even though it's only one character long. And so technically, this is an O of N operation of itself.
Okay.
But if we say like .chars.each or something like that, we would typically just say, okay, well, let's imagine that we split this out into two things. So we have an array of our characters, and then we're doing like an array.each. Because both of these are ON operations, we would only count that one time as an ON step. And because the chars is what we call a transient data structure, like we're just using this really briefly and then it immediately gets cleaned up. We're not using this as like we did down here where we're purposely tracking something in a hash. A transient array like this, we don't count towards our space complexity either.
Okay.
So if we were doing like chars.each, we would still say this is an ON operation and we're just iterating over the data. We would just say, okay, well, you're just iterating over what you have because we're just throwing that array out as soon as this loop finishes anyway.
I had one other small question.
Go ahead.
In these technical interviews with problems like this, should we be aiming to not use like outside libraries or enumerables and instead like kind of hand rolling our own stuff? Like instead of using a .reverse, we'd hand roll what the .reverse method would do. Is that right?
That's a great question. I would say always clarify with the interviewer whether you can use built-in functions. Generally, you're not going to be able to use like third-party libraries. They want to know that you can do things like just using the standard library of your language. So like, for JavaScript developers, you're probably not going to get to use jQuery or Lodash or something like that. And in Ruby, you're not going to be able to pull in like third-party gems, but you can use anything built into the language itself generally. But always ask the interviewer if like, do you want me to implement like a string reversal on my own, or can I just do .reverse on that string? And they'll tell you what's allowed or not. Cool. All right. Well, let's get to a second problem, and then I'll let you have your morning back. How's that? Sound good? So as far as this particular problem, O of N, that's the best time complexity we can come up with here. We could say like for each character, go through the string and try to find another matching character, and then keep track of like how many odd numbers we found, similar to what we were doing down here. That would be an O(n) squared algorithm, because for each character, we're looking through the rest of the array. And then for the next character, we're looking through the rest of the array. And for the next character, we're looking through the rest of the array. And so we would say that that's an n squared operation. That, though, would not use additional space. And so we could say we could do like a nested operation. This would be O(n) squared, but it's constant space, because we're not adding any additional memory complexity to track anything. We're just using variables to count like how many times we saw like an even count versus an odd count. And so these are trade-offs that we make as software developers. Do we optimize for speed, or do we optimize for memory usage? And that's also a good question to ask your interviewer. Do you want me to optimize for time complexity or space complexity? They'll probably, like most of the time, I'd say probably 95% of the time, tell you to optimize for time and not for space. So most interviewers are okay with using more memory to get a reduced time complexity. And so that should always be your goal. Like, can I store something a little extra to reduce my overall time complexity? Cool. All right. So I'm going to drop another poll in here, and we're going to do one of the other 3 remaining ones. So we have pick 2 numbers that add up to a target sum, or find a duplicate value in an array, or find a common element in many arrays. Ooh, voting on this one's also really close. All right, there we go. We have a clear winner. We're going to go find a duplicate number in a large array. So let me go get the prompt for that one. And I will send you back to the same breakout rooms as soon as I find that prompt. It's not there. Where is my other? There it is. All right, so finding a duplicate number. And I will drop this in your channel as well. So here's your second problem. And that's in your Slack channels. So you have an array. It has all of the numbers from 1 to 1,000,000, but it's shuffled. It's randomized. So they're not ordered sequentially. And one of the numbers between 1 and 1,000,000 is in there twice. So technically you've got an array of 1,000,001 things. How would you find the duplicate value? Now, I will say this. If you know the answer to this, don't bring it up with your team. Like let the other folks in the breakout room like try to figure out different ways of solving this. And we'll talk about the optimal answer for this afterwards. So if you know the optimal answer, we'll talk about that at the end. But in the meantime, let folks try to figure this one out. And then we'll come back in another 6 minutes and we will go from there. Actually, do y'all want the same rooms or do you want new partners? Drop in chat. Do you want the same room or new people? 1 vote for same. Same folks. All right. Same is fine. Okay, here come your same rooms then. All right, welcome back. So these 2 challenges that you've worked through are very indicative of the kinds of technical challenges you could face in an interview. And the reason that I only gave you a couple of minutes to think through the high-level code is because that's generally how much time you want to take to come up with that high-level design and that high-level pseudocode. Generally, you don't want to take much more time than that just to think of those high-level steps. Plan out that design, ask the interviewer, like, does this approach sound okay? Does this look okay? Do you want me to get started? If they spot a problem in that pseudocode, they'll tell you. But generally, that's approximately the amount of time you want to take to come up with an idea, come up with some pseudocode, jot that stuff down, ask the interviewer, does this look okay? If you're at that stage of an interview, they will be completely honest with you and they'll tell you what they like or what they, what they're concerned about in your algorithm. But generally, you don't want to take much more time than that because the rest of the time you're actually going to spend writing the code. So let's call on a couple of rooms here. So we're going to go to room number 5. Room number 5 is Jeff, Matt, and Will. What'd y'all come up with for an algorithm here?
So I think the way that I thought about it is I would sort the numbers from smallest to largest, and then I would iterate over that entire sorted array. And I would check to see if index equals index plus 1. And you should hopefully come across it at some point because they should be next to each other if they're sorted.
Yep. Okay, so as we iterate over the numbers, we're going to look at our neighbor basically at that point. All right, cool. Well, let's indent this stuff a little bit more here. So if we were to sort all these numbers in ascending order, what is the time complexity of our sort operation? What's our time complexity of a sorting algorithm? And we'll just use the best sorting algorithm that we have available. What's our typical time complexity there?
It's just a loop, right? So it would be O of n, or?
No, for a sorting algorithm, because it's doing a lot of operations to figure out what order to put them into. So if we kind of come back to here and we think about this one right here. So it's going to be our linearismic time. It's going to be n log of n, and that's going to be our sorting algorithms. So it'll be linearismic time to sort. So I pull that back up here. So this is going to be O n log of n, just to sort our data. Now iterating over those numbers, what's our time complexity on that going to be?
Would it be O of n?
Yep. So a lot of folks are saying it's just linear, which is correct. So that's just an O n operation. Now to look at our neighbor, because we know which position we're in order to look at our neighbor, we know our index position, therefore we know the next index position. So what kind of operation would it be to go look at our neighbor? So we know the index position in an array. What's our time complexity for that?
Constant time?
It is constant time, yeah. So that's going to be an O1 constant operation. And so now the way that I do this is whenever I have something nested, we multiply these two time complexities together. So n times 1 is just n. So it kind of cancels this out here. And so then, because these operations are happening at, like I call the same indentation level, we just pick the worst one of these. So which of those is worst? So we're going to sort and compare. So what are we looking at here? Which one is our worst operation between n log n or n? Which one of those is the worst time complexity? N log of n is worse, yeah. So our time complexity on this algorithm is going to be n log n. And our space complexity, now we're not really building a new data structure because we're just sorting what's there. It's probably going to sort in place. We're not purposely tracking this data in another data structure. And so we would just say it's constant space because we're just replacing what we had. And so we're not increasing our space complexity. So we're not using any more RAM, but we are sorting the data. And so that does increase our time complexity a little bit here. So I'll write that out as n log of n, and our space complexity is just O of 1. Cool. All right. Thanks, room 5. Let's go to room number 18. Room number 18 is Jackson and Jesus. What'd you come up with?
Do you want to go, Jesus, or?
Sure, we did pretty much exactly kind of the same thing. So
okay,
sorting the array and then just looking at the two elements that are coming in, and then if they're equal, then you pretty much have the return value. Otherwise, keep grabbing the next element, check again, keep doing that whole loop.
Yep. Okay, cool. And it's okay if you come up with the same answer. Again, any answer you come up with that's going to solve the problem is a good answer. So that's fine. Let's do one more room here. Room number 6. Room number 6 is Annie, Doug, and Elizabeth. Anything different?
Yeah, we kind of came up with something that we knew was quite inefficient. We were trying to think of a better way to do it.
That's okay. Inefficient's fine. What do you get?
Basically, we would take iterate over the array and basically compare it to the array for a match.
Yep. So compare to the rest of the array, and then inside of that, we're going to look for a match. Cool. All right. So let's talk about these as far as time complexities go. So iterating over an array, what's our time complexity there? So it's our time complexity for iterating over an array. Yep, a lot of stuff dropping in chat. It is linear time. It is an ON operation. Now, to compare the rest of the array, we're basically reiterating over the rest of the array. Now, we could slice that array, and that slice is like a temporary kind of that transient data structure. So we're not really increasing our space complexity, but we are looking through the rest of the array at that point. So our worst case scenario is that the very first number that we look at, and remember, we got 1,000,001 things in here. So the first time we run this, we're saying for this first thing, go look at another 1,000,000 things. So they're pretty much the same size. And so we would say then that this is doing another linear operation because the value of n is pretty much the same. Towards the end of it, it's drastically different because, you know, those numbers are going to shrink over time, but you're effectively iterating over the same amount of data again. And so that would also be O of n. And then looking for a match, if my number from this loop matches this, that's just a comparison. And so that's a constant time operation. So then because these are all nested, we start multiplying these. So n times 1 is just n. And then n times n, technically that's 2n, but in this case, we would say that this is n squared. And so if we did a nested lookup, then this is what we would call an n squared algorithm. But we were able to keep our memory in check. And so we're not increasing our space complexity again. But this time complexity is a little bit worse than sorting and comparing because the sorting operation is actually more efficient than doing the nested lookup. So far our sort and compare method is a little bit better for us. Cool. Does anybody happen to know the optimal answer to this question? Or did anybody use math to solve this? Ben, what do you got for us?
I don't know. I didn't look up the exact answer, but it was just something that I was working through in my head. If you take the length of the array, at this point it's 1,000,000, and you divide it by 2, and that's your starting point. So you start at that index, and then you look forward for what. So like if you're in the middle, and you take that number as your value, and then you look forward in the array and see if you find it, and if not, you start at the middle and look backwards and see if you find it.
That's not really any different than starting at the beginning and just working until you find it. Plus the number, remember your original array is also randomly ordered, and so they're not sequential. And so just starting in the middle and looking forward. So one way you could do that would be to sort it, look at n divided by 2, and if that number in that position isn't what you expect it to be, then you at least know if it's the right half or the left half that has that duplicate. And then you could only walk half of the array, but by then you've already sorted the array, so you're still going to be n log n in that scenario. Someone dropped in chat, if you add like key value pairs where you track and just count until something ticks up to 2 and then you found it. So we could, if we did like a hash or object tracker. So this would give us a linear operation of, as we iterate over all the numbers, we put them in a hash. And then if we tick up that number to a 2, then we're done. But because we're adding additional memory, worst case scenario, we've got to put all those numbers in that hash of the object. We're actually increasing our memory. We're like 2x our memory usage because we're adding another whole data structure of the same size. Because worst case scenario, let's say they're all sorted and the duplicate number is 1,000,000. We got to put all the numbers up to 1,000,000 in there first before we detect that 1,000,000 was the duplicate. Let's go to Alexa and then Joel.
So I don't think my answer is the most efficient, but thinking of it as a math problem, since we know it's between 1 and 1,000,000, you can add the numbers from 1 to 1,000,000, I guess creating a new array or some sort of loop. And then you should be able to add your array, and the difference is the duplicate number.
So another thing to do here, and just to kind of prove out Alexa's theory, whenever you're in a technical challenge and like you got a million things, always give yourself a smaller sample and say, I've got 5 things. So we've got 1, 3, 2, 5, 4, and let's say 3 is in here a second time. So let's prove this out. We're going to add up all the numbers from 1 to 5. And that algorithm looks like the sum is going to be n times n plus 1. And we're going to divide all that by 2. So if we have the number of from 1 to 5, we say 5 times 6 is 30, divided by 2 is 15. So all the numbers from 1 to 5 add up to 15. Now, if we sum up what's in the array, we're going to get all the numbers from 1 to 5, which is 15, plus 3, which is 18. So the sum of what's actually in the array is 18. And if we subtract 18 from 15 or 15 from 18, we get the value of 3. And that tells us what the duplicate is. Now that you know the optimal answer, if you ever get this in a technical challenge, you should always be forthcoming and say, oh, we actually studied this in class. I know there's a math algorithm to solve it by adding up everything in the array. Interviewers will appreciate that, because if you're like, oh, let me pretend to think about this for a moment. What if we use math? If you don't have a math background, they're probably going to recognize pretty quickly that you've seen this problem before. And then it's not really going to count as having figured out the answer because you knew the answer to begin with. There is a variation of this question that says you got all the numbers from 1 to 1,000,000 and one of them's missing. How do you find it? Well, if we sort and compare, we could use the sort compare method and say, well, if we sort all the numbers and we compare ourselves to our neighbor, if the neighbor is much bigger than us, then we know that the number in between is the one that was missing. If we do the nested lookup, that's not going to help us because we don't know which number is missing. And our hash object tracker is also not going to help us because we're only counting what we actually see. And if something's missing, we're not going to find it. But if a number is missing, we know that all the numbers from 1 to 5 would add up to 15. In this case, these numbers are only going to add up to 11. So again, we can just subtract these numbers and it tells us which one was missing from our list. Someone dropped in chat, could we iterate through the array and push them into a set? So a set is like a unique array. You could push them into a set, and as you add it to a set, you get a true false whether or not it was added. And whichever one returns false, you know that one's the duplicate. But you're still iterating over the list and you're making a second copy. So that would still be an ON operation, but you're still duplicating your memory at that point, because again, worst case, it's the last thing in the array that's our duplicate. And so in this case, our math answer is O of n, and it's constant times space because we didn't add any new memory. We're just tracking variables at this point by doing some math operations. So in this case, math is the best answer. Not every interview problem is going to be math as the best answer, but in this case it was. Cool. If you're missing 2 numbers, so someone dropped in chat, what if you're missing 2 numbers? That would actually be a lot more complex because then you don't know which one is actually missing. You would have to do something like the sort and compare method. But then as you find that thing, then you're going to have to continue to iterate until you find the second thing. But that would still be an n log n operation as you sort and then like go through and try to find it. But you're still using constant space because you haven't added another array to do that. So if there were multiple numbers missing or multiple numbers duplicated, I would do the sort and compare operation. If 2 numbers were duplicated, you could use the hash tracker or the object tracker. You're still potentially doubling your space complexity. The nested lookup would only help again for the duplicate, but not missing numbers. Cool. All right. Well, I'll let you go from here. I'll give you some of your morning back. I hope this was helpful. What I like teaching about this class is just a little bit of the pseudocode, but also like taking a look at the pseudocode and showing how I look at big O notation. Again, we're just looking for just introductory sort of knowledge around quadratic time, logarithmic time, like those terms, so that as you're thinking about the algorithm that you write, If you're looking at the performance chart, you can get into things like profilers and things like that to find out where your bottlenecks are. You can go analyze that algorithm and figure out, is there a way that I could make this better? Am I looking something up over and over again that I don't need to? Could I use a cache or something like that to reduce the number of times I'm doing a step of instructions? So there are usually ways of optimizing our code that we can reduce the average runtime. Maybe not always the worst case runtime, but sometimes the average runtime, we can optimize our code that way. I'll get this video processed on YouTube. I'll drop it in that Google Doc, and I'll just note in your channels when the YouTube video is done. Cool. If you do have other questions on this, I'm happy to answer those. Again, you will get a second class in Mod 4 around big O notation. And you'll have lots of different technical challenges that you can work through. I do encourage you to practice this over intermission if possible, because it is really good to be able to speak to this in an interview. It will definitely set you apart in interview scenarios if you can speak to it. You don't have to be an expert on it, but just an introductory knowledge is really all you'll need to kind of knock their socks off. All right, I'll let you go from here. Thanks for hanging out. DM me anytime on Slack if you've got questions about this stuff, and we'll talk to you later on.
Thank you, Ian.
See you, everyone.
Thanks, Ian.
Thanks, Ian.
Thanks, Ian.
See you.
Thanks, Ian.
Ian, I had a question.